Hello everyone, welcome to our presentation at DSAA 2021 Hybrid Recommender System for Detection of Rare Cases applied to Pulsar candidate selection. In this paper, we address the problem of detection of rare cases, including when class overlapping is present. Briefly speaking, we propose a hybrid recommender system that uses a target rare case to state users' requirements, that is, case-based, and ranks the candidates based on their similarity with the target with the aid of a labeled benchmark, that is, content-based. We apply our approach on the radio pulsar candidate selection problem for detection of two types of rare cases, low signal-to-noise ratio pulsars and fast radio bursts. So first, I'd like to define the pulsar candidate selection problem, also known as pulsar searching. You may ask, what are pulsars? Pulsars are a type of neutron stars with fantastic astrophysical properties such as extremely high density, fast rotation, and high magnetization. When they rotate, they emit radio pulses. Because pulsars are very far away, their signals are very weak when we detect them on Earth. Therefore, we must use large radio telescopes to find them. Once we collect the radio voltage time series data, we feed them to the pulsar searching pipelines to look for pulsar signals. Generally speaking, pulsar searches can be divided into two categories, periodicity searches and single pulse searches, and our work focuses on detection of isolated single pulses in the time domain. On the right side, we show an example of single pulse search diagnostic plot. You can see that there are 4 subplots, and astronomers combine information from all 4 subplots to decide whether there is any pulsar signals observed. For example, in the bottom subplot, the black spindle shape are pulses, and the rest are noise and radio frequency interference. It is worth pointing out that because the sampling rate in the time domain is very high, conventional object detection approaches using computer vision are not appropriate for pulsar searching problem. On the other hand, because of the high cost of data collection, a high recall is strongly preferred in pulsar searches. Traditionally, pulsars are discovered through manually inspecting the diagnostic plots generated by the pulsar searching pipelines. One example would be the Pulsar Search Laboratory that involves many high school students across the United States. However, as more and more data are collected in recent pulsar surveys, manually inspecting all these plots becomes impractical. Therefore, previously, we developed a 2-stage single pulse search approaches that can automatically identify and classify the pulsar candidates. Although our approaches achieve with a fairly high recall and reasonably high precision, it turns out that we found some pulsars are more difficult to find than others due to problems such as within-class imbalance and class overlapping. These pulsars may form a subconcept within the pulsar class. And one example would be the weak pulsars shown on the left. It can be seen that especially in the bottom subplot, the pulses are plotted in red. They are so weak that it is very difficult to differentiate them from noise. On the other hand, astronomers are oftentimes more interested in rare cases. Once a rare case as this is discovered, as it often contains more information, astronomers tend to ask the following question: do similar candidates exist in the data? To answer this question, we present our hybrid recommender system. Specifically, our approach uses a target rare case to specify users' requirements. And we modify the similarity metric between feature values by taking outliers into account. We then weigh the features based on the labeled benchmark data. Specifically, we calculate the feature weight as the product of the dependence coefficient and the outlier score to improve users' interest inference. we have tested two different dependence coefficients, mutual information and the correlation coefficient. Phi k is different from the Pearson's correlation coefficient in that it can also detect the nonlinear correlation between variables. In this table, we show the features extracted from each Pulsar candidate. It is worth pointing out that these features can be of different data types and can have different distributions. Next, let's look at our benchmarks and experiments. We test our approaches on two types of rare cases, low signal-to-noise ratio pulsars, which from now on we will refer to as low SNR pulsars, and FRBs. However, because there are only a few low SNR pulsars and no FRBs at all in the benchmark, we generate simulated rare cases by removing pulses from real pulsars, as the one shown on the left. Specifically, for low SNR pulsars, we only keep 3 to 6 astrophysical pulses with peak SNR between 6 and 7 sigma. And for FRBs, we only keep one astrophysical pulse with peak SNR at least 8 sigma. We run our experiments for 30 times and report the average. Now let's look at our results. Our results for low SNR pulsars shows that it can be seen that the mutual information multiplied by the outlier score requires the smallest number of candidates to be inspected in order to detect all 9 pulsars. This shows that when there is class overlapping, treating rare features values as outliers improves the similarity between rare cases. In practice, one can expect to detect 8 out of 9 pulsars by inspecting the top 144 recommendations of each target case. On the other hand, the NDCG score is only 0.22 because of class overlapping. We also present the ranking of features by the weights. Our results shows that mutual information multiplied by the outlier score correctly assigns most weights to features that separate low SNR pulsars from bright pulsars, such as group max SNR, number of recurrences, etc. So for FRBs, it turns out that they are more distinguishable from non-astrophysical pulses than low SNR pulsars. And uniform weighting outperformed all other feature weighting methods. In practice, one can expect to find 8 out of 9 FRBs by inspecting the top 14 recommendations of each target. The NDCG score is also much higher at 0.61. Similarly, we present the ranking of features by their weights. Although uniform weighting what turned out to be the best, the second best weighting scheme, also phi k times z, also correctly assigns most weight to features that separate FRBs from regular pulses, such as the number of bright pulses detected, maximum XNR, etc. So in conclusion, our approach was able to detect both low SNR pulses and FRBs. It performs even better when there is close class overlapping. And we have made our code and the data available online. Although we only use the Pulsar candidate selection problem as an example, our approach can be used for detection of rare cases in other fields that also requires high recall and may face similar challenges such as within class imbalance and class overlapping. Thank you.